Greetings, everyone. I want to go over the review for a quiz on the Chinese remainder theorem. So I'm going to do two problems. One, I want to do a little bit bigger moduli, but I'll do only two of them. So let's say we want to solve this system. And for two, it's actually extremely simple, the calculations. And you can actually do what the book calls backtracking. But I want you to do the Chinese remainder theorem. Just want to quickly go over it. So remember, we have, this is M1 and M2, the moduli. This will be A1 and this will be A2. What else do we need? We need little m. That's the product of the order moduli, M1 times M2. So in this case, that is 99,000. Okay? And then capital M1 is the product of all the remaining ones. That's the simplest way of saying it. And that means, therefore, it is 99. And M2 is the product of all the remaining ones, that means 1,000. So for 2, it's actually just the other guy. Right? And then the last thing we have to calculate is y1 and y2. And those are given by the conditions that they have to be the inverses of this capital M1 mod little m1. So in this particular case, that would be 99 times y1 is equivalent to 1 mod 1,000. Okay? So how do we do this? That in turn is, we use Euclidean division. Euclidean algorithm to find the GCD and then work our way back. So let me do that. So 1,000, well, that is 10 times 99, which is 990, plus another 10, right? Okay, so remember, these are the numbers that we're going to have to keep track of. Be careful, there are two tens, and one of the tens is only important because it's the remainder. Then we do 99, that is 9 times 10, plus remainder 9. Okay, so now, that's 99, then 10, that is 1 times 9, plus 1, and here is already our GCD. So that's the forward part. Now the backward part is we solve back and keep replacing. So 1 is equal to circle 10 minus circle 9. Then I use the next equation to replace circle 9. So this becomes 10 minus, and that is 99 minus 9 times 10. Right? I bring this to the other side and replace 9 by this expression. Now I work this out, thinking of these tens as like terms. Okay, we have done a quiz on this, so I hope it all works well. So we get plus 10 times 10, be careful, right? Minus 99. And then we can use this 10 to replace this 10 here, so that will become 10 times 1,000 circled, minus 10 times 99 circled, minus 99. And we group together the 99, so that is 10 times 1,000. And then we have minus 10, that's minus 100, minus 1, so minus 101 times 99. Then we can verify that actually, if you subtract it, you get actually 1. And this is true, right? Because the left, this would be, this would be 10,000, this would be 9,999. Okay, so that's it. So this tells me what? So let me write again. So 1 is equal to 10 times 1,000 minus 101 times 99. Now, this is important, right? This is why with two moduli it's easier, but you have to be careful because they each appear in two different ways, right? So which is what? We need modulo 1,000, so we're going to do modulo 1,000 here. Sorry, what did I do here? Sorry. In my last, when I was explaining things, I circled the wrong one. We're solving for 99 here, sorry. So True, it is. They both are moduli, this one, but which one is it? We want modulo 1,000. So we're gonna, this is gonna be modulo 1,000 disappears, so we get 1 is the same as minus 101 times 99 modulo 1,000. So this tells me that y1 is equivalent to minus 101. That's the inverse here, mod 1,000. Now, unfortunately, it's not. It is necessary for. Sorry, it is necessary. So I shouldn't say that. It is necessary for this thing to work well. That we need the y1 to be the actual remainder. So remember, this y1 has to be in z 1,000. So between 0 and 999. So we have to make this positive by adding another 1,000. So this would be therefore 899, right? Yes, 899. So y1 is 899 because I need to make it positive. Okay. So what about y2? Y2, that's going to be much quicker. Has to be equivalent to 1 mod little m2. So y2, capital M2 is 1,000, so 1,000 times this is equivalent to 1 mod 99. So by the 1,000 mod 99, it's not so hard to see, but let's quickly do it. We can already reduce that number, right? That is, sorry. So 1,000 divided by 99, that is 10 times. So we see that, so 1,000 is 10 times 99, that is 990 plus 10. Well, we actually have the same calculation before here. So we know that 1,000 is the same as 10 mod 99. Okay? We can always reduce mod 99. So now we're working with mod 99. I know it's confusing. The 1,000 and 99 have now actually different roles. So what we're now going to do, that's why I need to reduce this, I have to find the inverse of 10 mod 99. This means I'm going to do 99 is 9 times 10 plus 9. That will be my remainder. And then 10 is equal to 1 times 9. Let me write it. Plus 1, and this is my GCD. So I can solve for that. That is 10 minus 9. And then use this to rewrite this. This is 10 minus 99 circled minus 9 times 10 circled. The minus comes from the fact that I bring this over to there, right? But then I gather the like terms. I have 10 times 10 minus 99. Now this is something you might have immediately recognized, that actually 10 is the inverse of itself. Right, so let me say, right, so I said perhaps a little bit too quick. Let me write it down here. What can we do with this? Well, we need to work mod 99. Okay, so mod 99. So this part disappears, and we see that 10 times 10 is 100, which is equivalent to 1 mod 99. So the inverse of 10 mod 99 is 10. Okay, so we have that this is 10. All right, that is very good. So we are almost there. Let me erase now everything here. So what needs to be done now is to put it all together. The last step is the formula that you have. And that is where the AIs are used. So at this point, we have not used the AIs yet. So this is something that a lot of people get confused by and start using it way too early. Okay, so it's not hard. You just have to follow all the steps in the right order. Okay, let me get rid of all this. Okay, so what is x? The formula for x is a1 times capital M1 M1 plus A2 times capital M2 Y2. Okay. So, A1 is 5, capital M1 is 99, and little y1 is 899. Plus A2, that is 11, capital M2 is 1,000, and y2 is 10. Now, what do? We calculate this modulo this little m, which is 99,000. Okay, so we just have to, at this point, modular calculation have kind of stopped. Now the big numbers come in. That's what I meant. My 5 times 99 times 899. So this thing is 400. y4 45,005, and the other one is 110,000. Okay, so the whole thing is 555005, and now we have to do this mod 99,000. That looks tremendous, big numbers, but just not. There are a lot of zeros here, so so let's quickly fill out what that is. 555005 divided by 99000. That is 5. So we can write this here as 5 times 99,000. So what is that? 99,000 times 5, that is 495,000. This is 495,000, this number. So what is remains? Minus 555005, and that is 60,005. So the solution is, this is the number. Okay, so this is equivalent to 60,005 mod 99,000. And the Chinese-Remainder theorem is exactly one solution of this system that is between 0 and 99,000 minus 1. Okay, and that's the solution, 60,005. Okay, that's one. Let me do another one. Okay. Sorry, I'm thinking of changing the problem a little bit here. Okay, I'll do one with 4. I haven't prepared it well, but I think it's good to see something how it works with 4. Although you'll see, so what I want to do, x is equivalent to 5 modulo 101. X is equivalent to 2 mod 7. X is equivalent to 3 mod 10. And x is equivalent to 0 mod 11. Okay. So let's work out what we have. What is little m? So this is m1, so let's write it. When you do this, indicate clearly which choices you make, because, okay, I've written in this order, but nobody forces you to do it in that order, right? You could have taken x equivalent to 2 mod 7 as your first equation, and then 7 would be m1. That's you can do whatever you want there. So always be very clear, mark very clearly what are the things that you are considering. So what is this? This is the product of all 4. Okay, so let's calculate this. That is 101 times 7 times 10 times 11, that is 77,000, well, we'll write it down, is 77770. Okay, so that's going to be our little m. Now we need also capital M, that is the product of everything else, that is 770, that is 7 times 10 times 11. Capital M2, that will be, okay, that probably I have to calculate this, 110 times 101, that is 11,000. 1110 M3, that is 7777, and then finally M4, that is what is M4? That is 101 times 70, that is 770. No, that cannot be, sorry. 70 times 101, 7070, sorry. Yeah, I better have the right things here, otherwise I'm getting myself in trouble. Now, what I also now need is y1, y2, y3, and y4. But I want to start with something that I normally don't do, but let's look at this. We know that this is going to be given by the formula a1, capital A1, y1, plus a2, capital M2, y2, plus a3, capital M3, y3, plus a4, capital M4, y4. But So this is A1, this is A2. Why am I doing this? Because I want to pay attention to this last one here. This is 0. So this term will not be calculated. So I don't need to calculate M4. Well, that's not such a big deal, but especially I don't need Y4. So I don't need this, right? We know that this will be modulo this 70,770 minus modulo this big modulus here, right? This guy. So, but I don't need this. That is the cute thing. If you have something that is where it has to be, what does it mean? We need to make this divisible by 11, right? If x is equivalent to 0, mod 11, it means x is divisible by 11. Now you might say, yeah, but how are you guaranteed that's going to be divisible by 11? Well, think a bit about it. 11 sits in here because, remember, these three guys are the product of the remaining ones. And 11 is always one of the remaining ones, right? It's the fourth one, so it's not 1, it's not the second, third. So each of these numbers are divisible by 11, so this whole thing will be divisible by 11 by the properties of divisibility. If you take a linear combination of things that are divisible by 11, then this thing will be divisible by 11. So that's the beauty of this. If they have a 0 here, you don't actually need to calculate it. So that's why I want to do one with 4. Although it's still going to be, of course, the other ones are a little bit messy, so let's calculate them. So I have to calculate yi times mi is equivalent to 1 mod little mi. Okay, just reminding me what I have to do. So if y is 1, then it's y1 times 770 is equivalent to 1 modulo 101. Now 770, so that's, you see, although these numbers, the big m's are very big numbers, our modulo are very small, so that we can immediately reduce this seemingly big number, divide it, right. So we know that 770 is 7 times 101, that's 707, plus 63. Right? This is 707 plus 63, that is 770. So this means, okay, okay. Let me write it this way. So this is equivalent to 63 times y1 modulo 101. So we still have to find the inverse of 63 modulo 101. Sorry, I wanted to erase this. All right, division algorithm. So 101, that's 63 goes in there one time. And then we have left 38. 38. And 63, that is 38, it goes in there once. And then we have left 25, 50, yeah, okay. Then 38 is 1 times 25 plus 13. And then 25 is 1 times 13 plus 12. And now we're going to be there, right? 13 is 1 times 12 plus 1. Okay? So 1 is the GCD, as it has to be. If I don't get 1 here, something went wrong. So this is 13 minus 12, using this 12. This is the same as 13 minus 25 minus 13. So if I take the minus 13 and another 13, so it's 2 times 13 minus 25. I'm going to replace 13 now. That is 2 times 38 minus 25 minus 25. So that is equal to 2 times 38 minus 2 minus 3 times 25. And we use now 25, so that is 2 times, well, let's do it here. 2 times 38 minus 3 times 63 minus 38. Where am I? Okay, so if I combine this, I have a 2 and a minus 3, so altogether 5. 5 times 38 minus 3 times 63. And then finally, I can replace the 38 by using this one. That is 5 times 101 minus 63 minus 3 times 63. So this is 5 times 101 minus 5 minus 8 times 63. Good. So what do we want? We want to do this modulo 101. So we have 1, and let me write it one more time here, we have found this one. Just let me double check, because I never trust myself. 8 times 63, that is, 8 times 63 is 504, and the other side 5, so yes, that is correct. So if we now work modulo 101, then this goes away, and so we find this is minus 8 times 63. So the inverse is minus 8, so y1 is equivalent to minus 8, but we don't want a negative number, so we have to add 101 to it, that is 93, very low. That is 93 mod 101. So I repeat, when you have a negative number, you have to find the remainder modulo 101. But this number is almost there, right? That is what you do with negative degrees. You put another 360 degrees to make it into a positive degrees. If you work with degrees, because that is working modulo 360. It's the same thing here. So minus 8, you add another 101 and you get 93. Okay, so the first one is 93. And now we have to do the second one. I'm going to erase this. Let me get a bigger eraser here. Now that goes bigger. Okay. Okay, so now y2 times this huge modulus, 11,000, no, not modulus, it's big M, and that is modulo 7. Well, that is nothing, because what is 11 divided by 7? That is, so this number 11,110 is 1,500, this times 7, 1587 times 7 is 11,109, so this is plus 1, so this is just equivalent to 1. This number is just equivalent to 1 modulo 7, okay, and so I'm there. Y2 is, y2 times 1, it has to be equivalent to 1 mod 7. Well, that means y2 is 1. That was quick. Y3, and that's going to be the same because it's also a rather small modulus, right? So y3, let me do it here. We have y3 times capital M3. Oh, let me write down what capital M3 is. Capital M3 is 7777. It almost sounds like I lived for a while. My wife worked in Columbus, Ohio, and that was the number of the taxi cab. Well, a couple more sevens, but it reminded me of that. Y3777777, whatever, is has to be equivalent to 1 modulo, what's the modulus? M3 is 10. Oh, but that's very easy. 7 is equivalent to y3, not 1, 10, right? The remainder modulo 10 is just the last digit, okay? And so what is the inverse here? Well, let's just try another. 1 times 7, 2 times 7 is 14, 3 times 7, 3 times 7 is 21. So if I do y3, then I get 3 times 7, that is 21, which is equivalent to 1 mod 10. So here is no calculation necessary. I see immediately it has to be 3. So y3 is 3. Okay, great. So again, let me get rid. No, not this one. These guys now, because this is the last formula I need, right? So let's wipe it up. So x is equivalent to this huge modulus, 7770, to what? A1, which is 5, capital M1, which is 770, and y1 was 93, plus A2, that was 2, capital M2 was 11,110 times y2, that was 1, so that's I don't want to write that. Okay. Plus A3 is 3, and capital M3 is 77, that's 7777 guy, and then y3 was 3 again. Okay, and that is the number I have to calculate. This one I have to do with a calculator. There's nothing else I can do here. So 5 times 770 times 93, that is 300. This is 385,050. This is, we can do this by in our head, right? And the other one I have to do is 9 times 7,777. That is 69,993. So if I add all this, remember this one has 0 in it, A4, and therefore I didn't need to calculate. That's the whole point. I wanted to do it before I did the calculation. Now the calculation is not going to be that hard either because modulo 11 is a small modulus, but you know, always better lazy than no, that's not, I don't know what the expression is, but okay, so here we go. Right, so okay, so we add this 358,050 plus 2220. No. Oh, I missed the 220 plus 69,993 is, this is supposed to be 450,263. Now we have to take this modulo this 77,770. So we divide this by 77770. So 450,263 is 5 times 77770. So 5 times 77770. That is 388,850. So that is 388,850. So what am I missing? Minus 450,263 is 61,413. Okay, so that I claim is my answer. Now I want to show you that you can actually also check this model using, for instance, Wolfram alpha. So let's see. So I have to not jot this down here. So this is also that 0 equivalent to mod 11. Okay. That you can actually check these answers, but again, not on the test, please. Okay. And in any case, I have to see all the calculations, right? So let's go to Wolfram alpha. No, I don't have Wolfram alpha yet. Here's Wolfram alpha. Now, how do you put this into Wolfram alpha? Well, as simple as you can think of it. Just write, okay, what do we have? What were the equations? X had to be equivalent. Now, equivalent, just write 5 mod 101, comma. So I'm going to write each of these equations separately, and he will interpret this as a system of equations that he has to solve modulo the modules that I gave. So x is 2 modulo 7, x is 3 modulo 10, and then finally x is 0 modulo 11. Let's see. Here's a hard time with this. It's the first time I've seen him work this long. Uh-oh. Oh, I see. I wrote a capital X here. This is my stupid iPad. Automatically puts everything in cap, and that might be the reason that he is getting confused here. No cap. Okay. See? So he says, is this what you want to do? Input interpretation, right? Solve this system. Yes, it's exactly what I want to do. And the answer is 614113. And I'm having my hands up and down here because it's the right answer. Okay. All right. So that's the quiz.